Hello, today we're going to compute the triple integral over e of x, where e is bounded by some paraboloid, x equals 4y squared plus 4z squared, and some planes, x equals 4. To visualize this, we have our y, x, z axis with a plane at 4, and so if you imagine some plane running along here, and then a paraboloid opening it up towards positive x and intersecting with this plane at some circle. It's probably what it's going to be, and we could verify that, but that's kind of the intuition of where it intersects, some plane at 4. So the intersection would be at 4y squared plus 4z squared equals 4, right? That's from setting these equal to each other. And then what you have is y squared plus a z squared equals 1. So it's a circle with a radius of 1, but it's not projected on the xy axis. It's instead projected on the yz axis. So if we imagine our, or not axis, plane, my apologies, YZ plane, it would look something like that. A circle with a radius of 1. And if we're dealing with something circular, symmetric about some central point, the x-axis, I'm immediately thinking, okay, this is probably a good use for a cylindrical system. But it's not going to be the typical cylindrical system that we typically use, where we have dz, dr, d theta. Instead, it's actually going to be dx, because x is that plane that we're following along, that axis that we're following along, right? So we could define y as, so if you're imagining given some theta, our y value would be the radius times cosine of theta. Z would be the radius times sine of theta, and then x would just be x in a cylindrical system. So it's not typical, it's defined a bit differently. And then from here, what other observations could we make? Well, we know that we have the intersection, or we could also state our Pythagorean theorem, y squared plus z squared equals 1, because we're on the yz plane. So also, sorry, y squared plus z squared equals our radius squared. So from here, we can observe that our range, so a circle with radius 1 on x, nope, it's not on the xy plane, it's on the yz plane, we could say is defined as some r theta, where r ranges from 0 to what? To, well, 1, right? Because our intersection is a radius of 1. And theta, full circle, it's going to go from 0 to 2 pi. So, and then what is the other range? Well, it's the range for x. And, well, x is defined as either 4y squared plus 4z squared, or we could define it as x equaling 4, and let's factor out the 4, and then we're left with y squared plus z squared. And if we're defining in our cylindrical system that our radius is y squared plus z squared, we could define x as being 4r squared. And then from here, well, x would just be that constant 4, as well in the other cylindrical or polar form. So our lower bound would be 4r squared, and our upper bound would be the plane at 4. And then, like we said from earlier, our radius is ranging from 0 to 1, and our theta is ranging from 0 to 2 pi. And we need to, first we have x. Well, x is still x. We're iterating over x, but let's not forget, since we're in a polar system, or since we're in cylindrical coordinates, we need to scale by r to account for that change of the change of system. We're doing a linear transform to a different system, so we multiply by r, and then we have dx, dr, d theta. From here, this integral isn't too difficult. So from 0 to 2 pi of d theta, nothing else is relying on theta, or will generate a function of theta. So we can just say that that would just be 2 theta if we evaluated 0 to 2 theta d theta. Then we have the integral from 0 to 1, and let's integrate. Well, the r is a constant multiple in this inner function, so we could factor it out, but now we use our just our general power rule for evaluating this integral. So x raised to the second power divided by 2. So we could just factor that constant multiple. And then x is ranging from 4r squared to 4 dr. And then we could just evaluate this integral. So we have 4 squared minus 4r squared dr. And then from here, it's mostly a simple algebra. And then we could factor out 16, a constant multiple. And then this is another simple power rule. So 16 pi, and then it's that same case where it's upper bound is 1, the lower bound 0, so we just evaluate it 1. And then a half minus a sixth is a third, so 1/3, so 16 pi over 3. So that simplifies. Oh, no, it doesn't simplify. That's our solution. So, yep, that's how you could compute this integral. It's pretty interesting because typically, the reason I'm showcasing this example is because typically when we're thinking of a polar region or a cylindrical region, we're thinking of it being upper, or we're thinking, most of the examples that you probably see only have an axis of symmetry with a z, but that doesn't necessarily need to be the case. As long as it has a axis of symmetry, and that's what you're kind of integrating over, right? So, yeah. So, and then you could also define your system with y, x, z differently. So that's this example.